Yeah, I will continue from the last theorem I stated yesterday. I will explain what's going on using simple words. So, say we are given a probability and measure preserving system where X mu is the probability space and T is the measure preserving transformation. So, and suppose phi is a function. And we fix a subsequence of integers, of positive integers. Then what we say is that it's something like this. I mean, I'm not saying it's always true. I'm just saying the last theorem I stated yesterday is like for mu, almost every point. If we consider the average, of this, then it converges to the space integral of mu. I assume that it's ergodic. Well, at first glance, probably you will feel that is that really possible for non-trivial dynamical system to have such kind of thing holds? I mean, let me say any. Say Rn is the piece prime. I mean, so Rn is the piece prime. Nth prime. Well, it's known that it's always true if, say, Rn equals n squared. It's a theorem of Bergan. Probably 1989, or maybe 88. Any questions? No, I'm not saying it's true for all. I'm saying it's true for the ergodic systems I wrote down yesterday. But I'm trying to say, what does it, I mean, so why should we believe such kind of thing holds for reasonable systems? Say X equals the interval, maybe, and then consider the big measure. And then we consider the time m map for integer m bigger than 2. Time m. Then this is true, because somehow this is a Bernoulli system. Bernoulli. So somehow this is just the shift, right? For shift, well, means shift one step and shift some Rn step, there is really no difference. If you believe that if something holds for times m map on the interval, then it should be true for the diagonal group action on the homogeneous space. Then it's believable. But yesterday, what I stated is a multiple version and with an error term. But I hope it clarifies something I stated yesterday. So the statement is false for, say, also the interval with the big measure, and then with, say, plus square root of 2. For this system, we don't have this kind of statement. Somehow, to have this kind of statement, we should have a mixing of all orders. So this system is not mixing, so it's not true. The statement, that means is it true that for any subsequence of integers, we have almost surely that it converges? For any, say, smooth functions, or maybe bounded? I think the convergence, even the convergence fails. This is about this is the explanation of this point. Now let me give a picture to explain the, say, two-ergodic theorem. Suppose the blackboard is the whole space, and then we have 2 points, say x and y, and we have 2 sides. One side is A, the other side is B. They're not necessarily disjoint. I draw disjoint just to make it easier to view. So the multiple ergodic theorem says that if we consider the trajectories of x, say under the time t, and the trajectory of y under the map S, then first it said that there are infinitely many n such that simultaneously they visit Tn x. Then simultaneously one trajectory is in A, the other is in B. Moreover, if we consider the asymptotics, so it's Tn in A and Sn in B, n bigger than 1, less than capital N, somehow the cardinality is asymptotic as n tends to infinity, capital N tends to infinity to mu A times mu B, and then times the capital number. That's what it is. That's what the two-ergodic theorem says. Okay, so today I'm going to review something from yesterday, and then I will try to generalize it to arbitrary homogeneous spaces. And then maybe I will prove some regularity theorems. Before I do that, are there any questions or comments? Okay. Let me give a brief review. I will start here. Yeah, if I will write the larger here and smaller in the middle. So, you have. What is unknown? Yes. You mean the general statement? For general statement, yes, it's unknown. But for some special cases, it's known. Okay, it's basically, that's a very good question. I would say the method to prove this is, here is the principle. The only tool I use to prove this kind of statement is effective, say, 2m multiple correlations. Then it implies somehow effective maybe I should call it random, because somehow I randomly choose a subsequence. Effective random M ergodic theorems. That means, of course, Bagan used a different approach. That's why he can prove a general theorem. The method we use is effective 2M multiple correlations. It's like effective 2M multiple mixing. So if you can prove something like that, then we can get something like this. That's the principle. Now let me review what we talked about yesterday. The aim is to give general results. Maybe I should erase actually. So let me give a quick review first. So yesterday we fixed a lattice in an arbitrary, say, connected Lie group G. And then we fix a special semi-simple subgroup H. Which is embedded in G. Then actually there is an somehow algebra going on here. Yesterday I fixed the weight. So here I will write the weight as an element of the Lie algebra. Actually it's a cone. So this A plus is A plus plays the same role as the weight yesterday. So it's but I will write it in the form of the algebras. So just the M numbers and N negative numbers. And assume that the trace is equal to 0, so that it belongs to the Lie algebra of H. The Lie algebra H is Gothic H. Any element, say W, in this cone, we fix a one-parameter subsemigroup denoted by FW equals AT equals exponential of TW with T non-negative. The philosophy here is that the dynamics of the H action on the homogeneous space G mod gamma is well understood. So we want to, through the dynamics of H action, to study the dynamics of this one-parameter group action. On the certain on certain orbits. So now let me fix a unipotent subgroup. I will write it as, well, yesterday we used some matrix notation. But now I want to interpret everything intrinsically using the Lie group theory. I consider it as an element of H with what? Okay, theta belongs to the matrices. And by matrices, then what we stated yesterday, we stated several results. The first one is it's the equidistribution of generic Let me draw some pictures to quickly remind you what does this mean. So basically, okay, we given a space, and then we fix a piece of orbit. Here is some piece of ux. Then we proved that for almost every point on this trajectory, it equidistributes if we study fwx. I mean, almost surely the trajectory of fwx equidistributes with respect to some homogeneous measure. You have a question? Oh, yeah. Thanks. Here is x belongs to G mod gamma. Then, in some special cases, we get effective versions. So now we assume that, in addition, G is H. In this case, we have somehow effective version. I will call it the effective Ergodic theorem. Somehow, maybe I should say Burkhoff type, because somebody uses Ergodic theorem. There are basically two types of interpretation. One is mean, the other is point mass. So here I mean Burkhoff type. Then we have central limit theorem. Central limit theorem for Burkhoff averages. Then somehow, Jean-Francois Kahn asked some questions. Then there is something I stated. Not very precisely, but I will try to state a precise version today. Somehow the regularity of cohomological equations. Then what? If time permits, I will give a proof here. Proof of part of this result. The reason is that it doesn't use any homogeneous dynamics. And then it's multiple pointwise Ergodic theorem. Actually, I should say it's a quantitative version. Quantitative. Now, the first thing I would like to do today is to say that all these results is true if we have a correct interpretation of this. Let me say give a simple non-compile Lie group. If we have the correct interpretation of A+, then everything just the same statement. Probably I will not give. Actually, it will be the first time I'm talking about the generalization of A to arbitrary homogeneous spaces. Because sometimes in ergodic theory seminars, I should avoid this theory and only using the examples. So here seems there are enough people interested probably in the Lie groups, so I should say something about it. So what's the general H? The general H is well, it's not difficult to set up a denotation of H. So the H should be a simple non-compact. Well, let's say this that is connected Lie group. I basically will write everything here in the general language of Lie groups. Now we have H. So what is before determining A, let me interpret what U is. U is the unipotent radical of a parabolic subgroup. So let P a proper parabolic subgroup of H. And let U be the unipotent radical of P. That's the correct setting, actually. Then somehow A is a cone, but it's a cone in a maximal split torus. So let's fix A, a subgroup of P. I will call it the maximal R-split torus. Maximal R-split. Somehow it's a mix of Lie group language and algebraic group language. But it's I'll say the connected component. And then A is the Lie algebra of this abelian connected Lie group. So what is the expanding cone? Let me give the definition. Now I'm trying to give the general definition of A+. Actually, this type of dynamics is studied extensively. As I said, due to its close connection to the finite approximations. But the general question is not studied quite often. Well, there are few studies because there is first, there is no motivation. Second, there is no general setup. What should be the A+? I mean, for what kind of A+ should we expect these type of things? The definition is we call the expanding cone of U in A is, I will call it AU plus. Here the graphic U is the algebra of the unit group U. Sorry, I should introduce more notation, but before writing it down explicitly, I need to introduce more notation here. Maybe let me do it here. So let B be the usual killing form under the algebra of H. Well, killing form is just the trace of the joint representation. And it's positive definite on the Lie algebra A. So it's actually an inner product on A. So let's fix. So let phi be the root system. Then we know that the Lie algebra U is a sum of root spaces. So it's a sum of, say, H alpha. So for the index set, it's important for us. It's I will denote it by phi U. And then for any alpha in phi U, there exists a unique S alpha in A with the following properties. If we compute the killing form of S alpha with any element S, then it's exactly the value of S at the value of R at S. Now I can write down the definition of the X-bounding cone. So it's just the positive linear combination of the S alpha. T alpha, S alpha. Its T alpha is positive. I claim that this X-bounding cone plays the same role as the cone here. Okay, so now it's the claim, maybe theorem, but theorem should be precise, but so I write down the claim. So all the results are previous. Non-trivial Lie subgroups. I mean, it's an arbitrary parabolic subgroup. It could be the minimal and could be the maximal. So when it's minimal, well, it depends on what we mean by non-trivial Lie subgroup. I mean, then the Lie subgroup here is abelian. Here, arbitrary parabolic subgroup, not equal to H. The example, well, here, that example is a kind of a maximal parabolic, but minimal idempotent. I mean, it's could be maximal could be up, could be. What? Okay. I should say maximal asymptotic torus of, I think it's the same, right? The maximal asymptotic torus of the parabolic subgroup is same as the maximal asymptotic torus of H. I think they're the same. If not the same, then just say of H. Are there any difference? No, I think it's the same. The maximum asymptotic of P and maximum asymptotic of H. The claim is all the previous results. Hold with A plus replaced by AU. No, I should not say that. AU plus 1, P is maximal. When P is maximal, and when P is not maximal, there's still some statements. Then, the same results also hold for some possibly proper AU plus tilde, which is possibly a proper cone of AU plus. But there's some algebraic condition that you can explicitly put on this cone. But I'm not going to go into details here. Let me mention some interesting problems. Question. Can we prove, the Shah type of results for curves in U? Recall that I stated a result of Nimi-Shah, m equals 1 or n equals 1. He proved that for analytic curves, it asymptotically equidistributes. Actually, he also proved some results for the rank 1 case. But for general case, it's not known. The typical thing is that, okay, we can give some abstract conditions so that that kind of results hold. But here it's kind of, the basic question is to describe this. Describe the curve using simple geometric describe the curve using simple geometric language. Well, I would say abstractions. Well, for Shah's theorem, he said non-planar analytic. in the Ronggang case, say SON1, it's non-planar, not circle, if I remember correctly, but maybe I'm wrong. Or in general, can we just describe the curve that satisfies the asymptotic equity distribution with some simple geometric abstractions, say not of some shape? Okay. Now I'm going to give pictures of the expanding cone. Okay, so I think I should call this 3.1. Okay, this should be 3.2. Now it's 3.3. Is pictures. I will give a picture using A2. So now we have this is the root system of A2, although I didn't draw it very well. This is epsilon1 minus epsilon2. This is epsilon2 minus epsilon3. So what do I mean by this? Actually, we have the Lie algebra is S1, S2, S3. I consider it as the element of SL3. Now, epsilon1, just the S1, epsilon1 minus epsilon2 is S1 minus S2. Just if we act on it, it's S1 minus S2. I consider them as positive roots, simple roots. Then it's epsilon1 minus epsilon3. Then it's the negative ones. Somehow, I have to draw the roots and the elements of the algebras in the same picture using the Killing form. Now let me draw the wave chambers. It should be a line, but it's not looks like a line. Why do I do that? Okay, now it looks like a line. Now it's the walls. These are the walls. Does it make sense? Yeah. So what are the? This is the wave chamber. For the particular choice of the simple system. So what is the cone? There are 3 parabolic subgroups. So for the maximum parabolic subgroup, this is one cone. And there is another cone. These are for two maximum. And for the minimal parabolic subgroup, it's just the union. Now I want to see the difference between the expanding cones defined there and the wave chambers. It's not the same as wave chambers. Just there's some overlaps, and there's something not in the wave chambers. Also, in some sense, this picture is misleading because somehow the cone for a bigger unipotent group is the union of the cone for the smaller unipotent group. In general, it's not true. That means that the cone for the bigger unipotent group is not always the union of the cone for the smaller unipotent group. So 3.4, I will call it the regularity theorem. Of Lipstick type. So let me state the result and then give a strategy of proofs and then give some details of some parts. So the theorem is about let the G be a connected semi-simple and no compact factors. And for simplicity, let's assume that it has a finite center. Well, it's a long assumption, but it's actually natural assumptions. Let's assume that the gamma is irreducible lattice. I will give the definition of irreducible lattice later. So assume that element A is add diagonalizable. And of infinite order. And suppose psi is a summation of a compactly supported smooth function at a constant. The conclusion is if phi is a measurable solution, to the cohomological equation then there exists a smooth function such that phi tilde equals phi almost everywhere. Well, first let me give you the definition of irreducible lattice. Smooth. Okay, there is this the smooth belongs to C infinity X. Thanks. That's the most important part. So let me give some remarks. So gamma is irreducible if and only if for any normal subgroup of G non-compact. We have the group N gamma is dense. That's the definition of irreducibility. Let me give you an example. So say SL2R times SL2R, then modulo SL2 square root of 2. Here, the embedding of square root of SL2 square root of 2, I should say, it should be a ring, should say a joint square root of 2. The embedding of this group is through Galois conjugates. So it is an example of irreducible lattice. So what A should be? What kind of A can be? So A could be, say, E minus 1, 0, 0, times the identity matrix. That's an example. But this theorem makes sense. You have one. Okay. So basically, if you think this is too complicated to read, you can simply think of this example. It contains everything new in this theorem. And gamma is irreducible is unnecessary. Just make the statement here simple and less technical. This is really the main example of this theorem. The second remark is co-compact and and the group generated by unstable Hauer spherical subgroups and the stable Hauer spherical subgroups is equal to G. I will give definitions later, just after I write it down. Then the theorem is due to Amy Wilkinson. So the unstable Hauer spherical subgroup is defined as the following: J plus equals we do the conjugations. And then it converges to the identity as n tends to infinity. Okay, just write this way. Then we can define the stable Hauer spherical subgroup in a similar way. But here is, and I should write down n tends to infinity, and a minus n tends to infinity. So what are they here? In this example, it's just I will write down the stable one. Then the stable is just the transpose of this one. Amy works on partially hyperbolic dynamical systems. So they don't use this language. They call it this condition in the partially hyperbolic dynamical system is called accessible. That means if the space is compact and the system, dynamical system is accessible, then it's due to Wilkinson. She proved much general results under the assumption of, say, partially hyperbolic, accessible, and bunched. But all the assumptions hold if gamma is co-compact. Next, let me outline the proof. There are several steps. In step 1, we show that there exists a function phi tilde such that phi tilde equals phi almost everywhere. Well, every time we make a improvement on the regularity. In the first one is in the first step we prove that phi tilde is smooth along almost every I call this group, maybe I should just write down, GA, J minus, I will denote it by J prime orbits. In the case the space is accessible, basically here we are done. But if the space is non-accessible, we need to do more things. Here we assume that phi is a manageable solution. So in the second step, if it's not accessible, we show that phi is square integrable with respect to the probability harm measure. Then in the step 3, I assume that well, it's not, I don't have to assume that, but to make the presentation simpler, I assume A is A1 for some one-parameter subgroup, one-parameter diagonal subgroup. Then we can define the centralizing subgroup. The centralizer of A in G is the elements commuting with A. Then in this step, we prove that there exists phi tilde, which equals phi almost everywhere, such that phi tilde is smooth along, or only one is enough, JC orbit. Now we are in a good position. We have proved that phi is somehow smooth along transversal orbits. It's kind of a standard technique from smooth dynamics is step 4. Using a theorem of Johannet, then theorem of Johannet, am I? Johannet's theorem implies that there exists phi tilde smooth. So what the Juhane theorem states, it states roughly speaking like this. Given two transversal foliations, if a function is uniformly smooth along each foliation, then the function is smooth. Uniformly smooth means the partial derivatives are bounded. That's step 4. Now I'm going to give a proof of step 1. Not using homogeneous dynamics. So proof of step 1. Actually, I will proof of step 1. For simplicity, let's assume G mod gamma equals SL2R modulo SL2Z. That means the space is accessible. So A is equal to this one. Then we have unstable Hausberg group. Somehow it has elements of this type. And we have stable Hausberg subgroup, which has elements of this type. I think I need somehow more spaces at some point. Let me just get more spaces. I'll erase the picture. Yeah, it's if I erase this place. Here the argument is inspired by the work of Wilkinson and Avila, Santa Maria, and Viana. What they do? They consider the bundle. X times R. Okay, X equals G mod gamma. So in their point of view, a function is a section. So the phi is a section of this bundle. That means they consider X to X times R, which X is mapped to X phi X. It's their point of view. So what they do next? Somehow they define a new dynamical system, the so-called school product. They construct a new system so-called school product from X times R, from this bundle to this bundle. I will call it T, which maps XS to X to AX, S plus psi X, psi S. Okay. Recall that psi is some fixed smooth function, and phi is the solution. What's the claim next? So the key lemma is the following. No, I cannot state the lemma for the moment because I need to introduce more notation, more machineries. Okay. Smooth dynamics, in smooth dynamics, one of the main tools is the stable foliations and unstable foliations. So, but the way they can get smooth, stable foliation and unstable foliation is through the dynamics on compact manifolds. But anyway, even though X is compact, so what they do is to pass it to a quotient, X tilde times R mod Z, and the map descends. This is compact. Now I'm using the approach of them. And then I will say briefly how to use the argument there in the possibly non-compact setting. Then they have stable foliations. They have stable foliations. Say they have stable foliations here, and then they lift it to the space X times R. So I will just say on X times R. That means for any point, there is a submanifold, one-dimensional. Which projects down to stable foliations on X. Well, in the homogeneous set, stable is can be directly written down. It's just GA minus X. The lift of the stable foliation on X allows us to define a holonomy map. So it's from X to UX. So for U belongs to GA minus. The holonomy map is a family of maps. It should be interpreted as a map from the fiber on X to the fiber on UX. The definition is through the lift. That means given X, maybe we draw it here. Okay, given X, and there is somehow UX. And then we lift the path here. This is X, And this is x, somehow it's hs. That's the holonomy map. The key lemma is as follows. If phi solve this cohomological equation, if phi is a measurable solution, then the section, what? That should be ux. Yes, yes, exactly. You're right. It should be ux. Then the section no, I would say somehow I will call the section graph. Is essentially H minus invariant. And similarly, it's also essentially H plus invariant. That means for there exists a full measure subset x prime, and if x and ux belongs to x prime, the u is in this unstable Hart spherical subgroup, then somehow the value of phi at ux is equal to the holonomy image of this phi. The similar statements holds if I put a plus here and a plus here, and also plus here. That means the graph is essentially stable holonomy invariant and essentially unstable holonomy invariant. There are two difficulties. One difficulty, the only difficulty to extend this argument to the non-compact case is how to define the holonomy map. How to define the holonomy map here. What I do is to write it down explicitly. Because the space is non-compact, there's no theory give us the stable manifold and unstable manifold. Probably not true. But we are in the homogeneous dynamic setting, so everything just explicit. So just write it down. I could write down the formula, but probably it's not worth for it. Basically, the main tool, okay, that's only one assumption, so we only use that assumption. I mean, so let me omit the details. So that, what do we do? So fix x. Somehow the theory of Lie groups says that, say, GA plus, GA minus. I think maybe I'm correct. I think 3 is enough. Contains the neighborhood of 0. I would say x in x prime. So basically, we define phi tilde locally, say on G plus G minus G plus, I will put a comma, a subscript 1 here. Just step by step. Here is x, then first it goes to G plus x, and then it goes to, I'll do it this way, G minus G plus x, and then it's finally go to what I want, G plus 1, G minus G plus x. So we fix the value of phi x. Here is, it should be h plus, then x, G plus x, then phi x. I keep doing this way. The final value is my phi tilde. The final value is my phi tilde. If it's smooth along stable and unstable orbits, then it gives a continuous function. Some part is missing here is that how to make sure that every point belongs to the good part, good set, which has full measure x prime. And there are some technical things, but that's the basic idea. And I think I'm out of time, so I will stop here. Thank you very much for your attention.
Maybe we can take one quick question, if anybody has one. If not, let's thank Ronggang once again.